Start up. Are we up? Yes, we are. Okay, cool. So, what we're going to start today is lumped element modeling. So, what we've done so far is that we've looked at the mechanical domain, and that was, um, diaphragms, cantilever beams. We also looked at a model where we would take some sort of accelerometer-like structure like this, and how did we model this if we wanted to draw some sort of simpler Moss type of problem instead of this
And
H thing?
statically indeterminate beam.
Yeah, it was something that was more like a clamped clamp beam that looks something like this. And how did we, first off, why are we allowed to do this? Remember, we have this giant area here. We have this giant area here for the structure. How do we justify converting from the giant H to the clamp beam? Anybody? Double fixed beam symmetry of the system. Well, yes and no. It is symmetric. Basically, remember that our square here, and I'll draw this in a different color. Our square is represented ultimately by some point load, some force that's acting over the square, over the proof mass or the floating element. What was the justification for why we're allowed to do that? I see Connor typing. Connor, you could also speak if you don't want to type. No, he's still typing.
That is true. It's we can just assume rigidity of the system and that the proof mass all moves at the same rate and
that's correct.
Uniform.
Yeah. So if you were to have this thing deflect, we'll see that the entirety of the structure, I didn't draw this perfectly, but because this whole thing is rigid, when it deflects up, the deflection, let's say delta of x, along that entire square is the same. So essentially, the delta x there will be the delta x at that point. So we don't need to model what's happening in between in the square region because of the fact that it all has the same deflection. The way that we account for that is by including this force that is possibly acting over the square from some external thing like an acceleration or some other type of thing. We don't need to know how the block deflects. We do need to know how the block deflects, but that will be what the deflection here is. So we would solve this clamp beam using Euler-Bernoulli or Castigliano's theorem, something we've talked about previously. And if we find the deflection at this point here, maybe that's at x is equal to L, that would be equivalent to how this entire mass moves up because of the fact that the deflection of that mass is exactly the same at every point, if we're assuming it's rigid. Mikhail, you can also speak if you want, if you don't want to type. But feel free to type, it's fine. Inside the block, I mean, not at the outside bits are why we can make the assumption. Inside the block, it just has the same exact deflection everywhere. We're assuming it's not twisting. Remember, if this is fixed on all four sides, based on the symmetry, it's going to be hard for this thing to deflect left or right in general because it's fixed on each side of those beams. And additionally, from a twisting perspective, there might be some twisting depending on how the beams are set up. But in general, we will neglect that case. So by assuming that the whole thing moves only up or down, and we model it as such here, where this beam can only move up or down, we'll say that the deflection at the center is identical to the deflection at the square and at the block. I hope that answers your question. So we did some law stuff, and then more recently we did circuit stuff. And we first discussed how no matter what type of element you have, if it's a resistor, a capacitor, or an inductor, they all are some sort of impedance. And the way that we try to help us is that if we have two impedances, regardless of what they are, in series, we know that they will add together to make some equivalent impedance. And then if they're in parallel, and again, it doesn't matter what these Z's are, this is true regardless of the Z's, our equivalent impedance was based on the reciprocal of those impedances. And if you find a common denominator when you have two impedances in parallel, you can write this as product. So the product of those impedances over the sum of those impedances. So this is product over sum. And that's typically what I remember when I think about reducing or simplifying circuits, is product over sum for two impedances in parallel. Any doubts so far? Thumbs up emojis are cool. Thank you for the thumbs up. Mikhail, is that a thumbs up or is that a question? Wrong button. Thumbs up. Cool. Thank you. So let's first remind ourselves, if we have an R, a C, and an L, what were the impedances? What's the impedance for a resistor?
R.
It's just R, right? What's the impedance for a capacitor?
1 over J omega C.
That's good. 1 over J omega C. And L?
J omega C.
J omega L, you mean?
Oh, yeah, my bad.
Yeah, J omega L. So no matter what these impedances are here, ZEQ is Z1 plus Z2, we would just plug in the corresponding equation for that impedance. So a lot of people try to memorize things like, oh, capacitors are the opposite of resistors, which is true in the sense of their mathematical behavior. But you don't need to memorize it if you just know that impedances in series add and impedances in parallel have this reciprocal nature. And then all the math works out accordingly. So we did that. You had some homework problems that are due Thursday that are based on combining impedances together. That's the first thing. Another thing we talked about was the idea of voltage drop, where if you want to have a circuit, with a bunch of impedances or something like that, and I want to know the voltage drop across this. This is V in over here. This is R. This is C. We know what was the analogy I gave in the last class, whenever that was.
Wasn't it like tolls?
Yeah, it was like tolls,
right?
That we have a certain amount of money that we start with, and we're going to spend some of that money on each of the impedances. So the voltage drop across each of those impedances will have to sum up to the input voltage, which means in general that V out will be less than V in, less than or equal to V in, depending on how small R is versus C. And if you have something in series, it's pretty nice because we'll do voltage division and say that the voltage output across the impedance of the capacitor will be some fraction of the voltage input that depends on the corresponding values of C and R, and also what frequency the input voltage is oscillating at. So this will be something like the impedance of the capacitor over the impedance of the resistor plus the impedance of the capacitor. Now let's just think about this before we plug in J's and omegas and stuff. If ZC is much bigger than ZR, that means that the toll is more expensive. You have to spend more money to get through this impedance. Remember, impedances restrict current flow. So if I want to pass it, that requires spending more money or spending more voltage. So if ZC is much greater than VR or than ZR, we say that V out is VN ZC. And if it's much greater than ZR, we'll just say that the denominator is simply ZC. So we see that we spend all of our voltage supplied by the input on that element because ZC is much greater than ZR. Does that make sense? Thank you. If ZC is much smaller than ZR, then we have the opposite type of behavior. If ZC is very, very tiny, this is essentially 0 in the denominator over ZR. Well, no voltage is used on the capacitor because it is a very low impedance. And again, we can plug in 1 over j omega c. We could just do that just to simplify it. 1 over j omega c r plus 1 over j omega c. That's just plugging in the impedance values. If you were to find a common denominator of this fraction, you'd have 1 over j omega c. For the denominator, we want to multiply the r by j omega c over j omega c. So we can add these together. So this would be j omega c r plus 1 over j omega c. And now we'll see that the j omega c's and the denominators cancel. We have 1 over 1 plus j omega rc. And that is our voltage output. And remember that ZC was 1 over j omega c. So if C is big, ZC is 0, or approximately 0 if it's really big. C is small, ZC is infinite. And we see that this equation that we derive follows suit, because if C is big, this whole denominator here is huge, which means that you have basically 0 voltage across the capacitor. As you have 1 over a really, really big number, it'll be a small fraction of the in because the impedance is low. You don't require as much money to overcome that toll. If C is small, we see we have an infinite impedance or a really large impedance. So if this is tiny, we'll see that this term might approach 0 or something like that. So you have 1 over 1. Most of the voltage is spent on the capacitor. Does that make sense? I wanted to review that kind of quickly just to remind ourselves about circuit stuff because it's been a little bit. How are we feeling? Any doubts or questions? I see some thumbs. Thank you for the thumbs. Cool. And the last thing we talked about was transformers, where essentially we'd have these 2 inductors that are coupled. And there's some ratio related to their voltages and currents. So if I say that the voltage drop across this inductor is V1, and I use stars to say that it is the voltage drop across the inductor, there's some current I1 star going through it. The voltage on the other side was V2 star, and then we had some I2 star. And these are assumed to be ideal inductors just for modeling purposes. In the real world, there's losses associated with this and all this stuff, but we're going to assume it's perfectly ideal because we're using it for lumped element modeling shortly. And the general idea was that if this ratio is written as 1 to phi, we say that the ratio of V1 to V2 star is 1 to phi, because this 1 is closer to the V1 star. So they will both go in the numerator of these fractions. So we see, if we do a little bit of math, that V1 star times phi is equal to V2 star. And if we assume that phi is bigger than 1, then we see that V2 star is bigger. We're basically increasing the voltage in the second part of the circuit. At what cost? What has to decrease to make this voltage increase? Somebody remind me.
Current.
What do you say?
I was gonna say current, but I
That's
don't think
correct.
that's
It is
right.
current. No, it's correct.
Yeah.
Because remember, power is conserved. If we assume that power is conserved, that means that we have I1 star, V1 star is equal to I2 star, V2 star. So if V2 star goes up, and this thing's a constant, well, that means that I2 star has to go down. And we can prove that mathematically like we did in class last time. Is that okay? Again, we're reviewing. I'm trying to go through this kind of quickly. But that's the general idea of where we left off. We also talked about impedance transformations, where we would move impedance to the other side, and that was based on the turns ratio squared, which will be important later. I'm not going to focus on it too much at the moment because I want to start notes at 10. But that's where we've been. That's where we've been for the last couple of weeks, reviewing mechanics of solids and reviewing circuits and introducing the concept of a transformer, all in preparation of lumped element modeling, which should be completely new to most of you. Some of you have seen this concept in vibrations, but we're going more in depth in this class. So this is note set number 10. This is on LEM, and that stands for lumped element modeling. And you've probably done this before without really knowing it in heat transfer. I think everybody has taken, most people, not everybody, have taken heat transfer in this class. But if you think back to heat transfer, and if you're looking at something like conduction through a wall, and let's say the wall is made of multiple materials, what was a way that we would take the concept of a wall and represent it differently? Does anybody remember how we would do that in heat transfer? I see a thumbs up. Connor, what is it?
Equivalent resistance.
Yeah, conduction has some sort of equivalent resistance. So if you think back to heat transfer, we had maybe some conduction problem, or maybe you have, material 1, and maybe you have some material here and some material here, and you're really hot. Over here, there's my fire, and over here, maybe it's cold or something like that at some other temperature. We would see these conductors modeled as equivalent resistances. And what we would ultimately do is draw a circuit representing the flow of heat. So you might have something like, you have this resistor that's associated with the material A, and then B and C are in parallel. Say I do T in and T out or something like that. Where the temperature is the thing driving the flow of heat. The resistance of the panels or the materials themselves are what is impeding the transfer of heat, depending on their conductivity or their size and things along those lines. And then we typically will look at this as a circuit where Tn is kind of like voltage and the resistors are representing some sort of hindrance to the flow of heat. Or we will literally say that this current is, I believe it's heat flux is the current. I don't remember off the top of my head, but that's basically lumped element modeling. We're taking some physical thermal system and drawing it as an electrical system. Now, these R's have specific equations based on the concept of conduction, depending on if you're using heat flux or heat. But we kind of remember from heat transfer there's some proportionality with thermal conductivity, with area, and inversely proportional to the length. And from that, you can figure out what your resistance is. This is the idea of lumped element modeling, and this is what we're going to focus on for the next couple weeks. In how do we take a system, a sensor or a transducer of some sort, that is very much a physical structure that moves in some way, that has electrical components with it. How do we model them in a way that is easy for us to understand? So LEM, the general definition, is that it's a tool used to understand the dynamic behavior for this class of transducers. And if we know the dynamic behavior of transducers in some way, we can determine important performance metrics like sensitivity, noise floor, minimum detectable signal, bandwidth, things we've talked about the first few weeks of class. So in order to derive what those things are or trying to model them or estimate what they will be, you can use lumped element modeling. A few things to note: this is not perfectly accurate. There are sometimes issues with this approximation, but I would say that you'll get 10% accuracy is kind of the rule of thumb that I learned when I was in school, which is a really good start from nothing. And then if you need to go to finite element analysis or something a little bit more complicated, you can. But starting with this is a huge step towards getting in the ballpark. And when you're thinking about 10%, you model this thing, you have an idea, like, oh, this is what I want my geometry to be. When you go fabricate it, are you going to be exactly that value? Like if I say I want my diaphragm to be 1.500 microns, is it going to be 1.500 microns? Exactly. Mikhail said it depends on the tolerances set. It does. You will never have a perfect dimension, especially in some sort of clean room where you're not dealing with, like, I don't know, a lathe or something where you can get like the exact value you want. There's still tolerances there, of course, too, with the machine accuracy. But when we talk about fabrication, you'll see there's a lot of chemistry going on. And you might want it to be 1.500, but it might be 1.49, which, depending on how accurate you want to be, may exceed 10% just from fabrication tolerances, depending on how much you're off. So by using lumped element modeling, it gives us a very good start towards getting to our optimal solution. So the general idea, though, is it true that once you start getting too small, you can't measure things properly? You can only create relationships between distances. I mean, there's definitely a limit as to how small you can go. This is one reason I like MEMS, because with MEMS, we can use a lot of the macro scale equations that we've seen in MOS, for example, where you have these giant beams. We can still utilize those equations, assuming that you're abiding by the other constraints. As you get smaller and smaller, of course, it gets more difficult to be as accurate because it's tough to work on tiny things, especially if you're going to like nano size. Like, that's really hard to do. I hope that answers your question. I don't know about the relationship between distances thing you're talking about, but we could talk about that offline. So the general idea is that we have some physical phenomena. So maybe, pressure causing a diaphragm to deflect or something along those lines. And what describes that is usually some sort of nonlinear partial differential equation, which is ugly. We don't really want to deal with nonlinear or especially partial differential equations. That gets very gross. So what we do is we will use LEM, and this will ultimately convert our partial differential equations into ordinary differential equations, which we know how to solve. Partial gets a little bit more complicated depending on what you're doing, and I don't think anyone in this class has had experience with partial differential equations, so focusing on ODEs goes a long way. That really does help us in the long run. Now, the question is, when are we allowed to do this? We say that this is valid when the wavelength of your specific input, let's say pressure, has some wavelength. And I'm not talking about in terms of the oscillations. Well, it is associated with the oscillations as well. But let's assume we're talking about distance, where you have pressure changing as a function of distance. And I'll show a picture in a second. If that wavelength is much greater than L, which is the length scale of the sensor, that will allow us to use Lunt-Thälmann modeling. So actually, I already wrote that down over there. So let me draw a picture to kind of explain this. Let's say let's say that this is X, and I have on here P for pressure. And I have some pressure that changes as a function of position. So if I'm sitting in this one spot, I hear a certain pressure, let's say. If I move back a bit, I hear a different pressure. It's changing as a function of position, the intensity of it, or things along those lines. So over here at this specific X, we have some high pressure. And over here, maybe we have some low pressure, depending on where you are positioned. It's all based on position, let's say. So let's say, that I take a microphone, which is very tiny. And first off, this is some P of X. And it has some wavelength, lambda. If I take a microphone, say that this is a microphone, and I want to measure the pressure at that location, if this high pressure is valid everywhere along this line, we'll see that that microphone is essentially just measuring that point because of the fact its length scale is much smaller than the wavelength. So we have a microphone that's very tiny, and over the entirety of the microphone, over the entire diaphragm, is a constant pressure. And that will be useful for us. So instead of drawing a free body diagram with this weird distributed load that changes as a function of position, we just have a constant distributed load, rectangular distributed load, that is based on the pressure that the entire microphone sees. I'm going to try to explain this in a different way in a second, but I want to see if there's any major confusion right now. Doubts? I see thumbs ups. Okay, that's good. I see one thumbs up. I see two thumbs ups. 2 out of like 20 is 10%. We're accurate for LEM. Come on. Anybody else? Are we okay? 10%. Woohoo. Okay, cool. Thank you. So, as an example, we're not going to focus on this equation in this class, but this is a really good example when you go into acoustics or things of that nature. So, as an example, if you look at the wave equation, the one-dimensional wave equation, it looks something like this. And again, we're not going to focus on what this means. But this is a PDE that describes the propagation of sound, assuming that it is one-dimensional. It's not some weird type of sound. It's just a planar wave. This is what we call the wave equation. I don't know about pressure density equation. I haven't heard of that for the whoever posted in the chat, Mikhail. So the benefit is, this is the PDE. If lambda is much greater than L, what is dpdx? Let's say if we're looking at the microphone, if I'm looking for dp over this region, is the pressure changing? PDE stands for partial differential equation. If you are to look at how the pressure changes as a function of x across the diaphragm, what do you think that is based on what I just mentioned up here? What is dpdx over this diaphragm? So if I start here versus here, how is the pressure changing across that diaphragm? It's 0. That's correct. dpdx is 0 in this situation, which means that our partial differential equation turns into an ODE, or rather two ODEs, because I also write that d squared p dx squared is also equal to 0, which makes our lives a lot easier. I hope that justification is nice, because dealing with the partial differential equation gets gross. But as soon as you assume that the wavelength of your pressure signal, let's say, is much greater than the length scale of the microphone, well, that allows us to reduce that PDE to an ordinary differential equation, an ODE, which we've had experience in solving in several of our classes already. We buying this so far? Basically, the big thing here is that lambda has to be much greater than L. If you start getting close and those numbers aren't as far away as you would like them to be, well, then you have issues with your modeling and it won't be as accurate. So that's kind of like an introduction, at least to when it is allowed. We're going to talk about now, what is it? But in terms of, I guess before we get to let's talk about some words that you might have heard in vibrations from me, is the concept of efforts and flows. And if we think back to electricity, what is the power of some sort of circuit? Let's say I say P electrical. In terms of current and voltage, let's say, what is the power generated? Yeah, it's IV. That's correct. This is I times the voltage drop across a component. You can see how much power is expended on a certain resistor or something like that, based on the current that goes through it, and the voltage drop that is acting across it. Now, if we go to the mechanical domain, what is power? Think back to physics 1, or maybe another class. Machine design might do it. I don't know. What's power for mechanical? I see Mikhail typing, and Charbel. I see T times W. What's T times W referring to? Torque?
Yeah.
Okay.
Torque
More
times the
frequency?
the arm length, or yeah, the angular shit. Yeah.
Yeah. What I'm more looking for is what Mikhail said, which is force times velocity. So I'm going to write velocity as x dot times force. And what's interesting is that if you look at this, we have I and x dot, where I flows through something and x dot is describing the motion of something, like the flow of the object moving back and forth, let's say. These are what we call our flow variables. And we'll say that something is moving in that situation. And that's correct. That's a really good point to bring up. I see that somebody just put in the chat. Is I, by definition, this I is the change of charge with respect to time, and x dot is the change of position with respect to time. You see that in these two different domains, even though they're completely different, they both have very similar equations. We see that the power is some flow times something, and the current is dq dt, the change of charge as a function of time, and velocity is the change of position as a function of time. Now, the other variables are the things that cause, these are what we call the efforts. They cause something to happen. Without this force, you won't have any velocity. Without this voltage, you won't have any current. So the efforts cause something to happen. We think of these as our cross variables. We think about voltage drop. It's a voltage drop across a component. And our flow we think about as being through variables, because current goes through a component. Is that okay? So what we see is that power is the product of a flow and a voltage. This is what we call conjugate power variables. This is like I and delta V. They're paired together. They're conjugate power variables. X dot and F. They're paired together. They create power when multiplied. Is that okay? Product of flow and effort. Oh, sorry, flow and not voltage. Effort. Voltage is an effort, but that's specific to the electrical domain. Thank you for that correction. And what you'll see is that we're going to ultimately take some sort of system, a mechanical system, or an acoustic system, which we'll talk about shortly, and represent it as an electrical circuit for our model, where the effort that is causing the mechanical model to move in some way, like an external force or an external pressure or something, that will be the same as a voltage source in the electrical circuit. That's our effort. We'll model it as a voltage source. So efforts are modeled as a voltage source. And then flows are modeled as a current. And I guess I'll say it's a voltage source, but you can look to see what portion of the force, let's say, is acting on the component doing effort division, which is basically voltage division. And we can figure out how much velocity is happening in a certain part through looking at the currents in the system and things along those lines. We'll see that sensitivity plays a role here because if I have an effort in the mechanical domain, like a force, and it's going to produce something in the electrical domain, like a voltage output, we will draw a circuit that goes from the mechanical domain to the electrical domain. And if we do circuit analysis on it, we can find the ratio between that input force and our output voltage. And that's what gives us sensitivity ultimately. This is the whole benefit of doing this, is that we can understand the flow of energy in the circuit, and we can use that elementary circuit analysis to find information about how the transducer performs as a function of frequency. So let's go ahead and just talk about what our plan is here. First off, we'll look at energies in the system. So if we have kinetic energy in the system or potential energy in the system, how can we use that to find some important parameters? We will find what are known as lumped elements that account for all the energy in the system. And I'll go into a lot more detail with this shortly. But the general idea is that if I have a system that is moving, like a diaphragm, let's say, that's oscillating, is there a way for me to represent that as like a spring mass damper system? Can I take the mass of the diaphragm and find some value that's associated with it that I can use in a spring mass damper system? And a spring mass damper system is very easy to model in the electrical domain. We'll talk about that later when we get in the next note set. But in general, we're going to look at energy and see if we can determine what kind of circuit element we'll use to model the behavior of that part. If that's confusing, don't worry. We're going to go into more detail shortly. After we can draw a lumped element circuit, that we can use to solve for performance metrics. And this will be in terms of variables. You'll have some diaphragm thickness or tether length or something along those lines, what material it's made out of, if it's made of silicon or something else. How can we, or what we'll do is draw that circuit, solve that circuit, and we can figure out what the behavior of the transducer will be within 10%. So in this note set, what we're going to do is determine the lumped elements. And in the next note set, we'll go ahead and look at how do we build a circuit after the fact. That's kind of our goal for this note set. I see Mikhail's typing, so I'll let him finish real quick. But what we're going to do in this note set is look at what we call a lumped mass. I'm going to keep going, Mikhail. You're taking too long with typing. When you say does it mean usually mean it depends on the situation. It's plus or minus 10%, I would say. The question was, when you say there's a within a 10% error, does it usually lean more on the plus 10% or minus 10% side on average? It depends. I honestly don't have a good answer for that. It depends on fabrication, mostly. It depends on what type of transducer you're looking at. I would say that there's no rhyme or reason that I can think of at the moment as to why one would be more or less than the other. From a fabrication perspective, which is easier to answer, if I make my diaphragm too big, we'll end up having a different behavior than if I made it too small. So if I etched a little bit versus a lot, that will change the behavior of the microphone, let's say. And that might be plus or minus 10%, depending on what direction you go in with that etch. And of course, there's lots of other things too that are involved. You have some sort of tolerance with all your circuit components that you use, any sort of hardware that you use. You might induce, and we may talk about this later, what's called packaging stress, where you're taking the die and you're putting it into some sort of cylindrical tubing or something like that. And during that process, maybe you heat it in a certain way, or maybe you tighten it in a weird way, and you end up inducing packaging stress, which causes a different behavior of the diaphragm. There's a lot that goes into this, is the point. So there's no real right or wrong answer there. But I'll say plus or minus 10% is good enough for what we're talking about. So when we think about vibrations, which is it's a co-rec for this class. This is arguably the most important thing in vibrations. Oh, why did I put R? Okay. This is arguably the most important thing in vibrations. You have some mass that some external force is acting on. It deflects. And depending on your damping in the system or your stiffness or the value of the mass, you will have different behaviors. I mean, probably the most important equation from that class is what? Vibrations, people, most important equation.
M over K.
Oh.
Go away.
Square root of K over M.
Thank you. Omega n, the natural frequency is the square root of K over M. And then damping will do what? If I have something like an underdamped system, how does it decay? Well, assume that the force is not there the whole time. Let's just say I have a free vibration system. I pull the mass, I let go. How does that displacement decay if it's underdamped?
Oscillating.
It oscillates. That's correct. If it is, it does exponentially decay, but it has a sinusoidal behavior as it exponentially decays if it's underdamped. If we're overdamped, you will have some sort of exponential decay without oscillations. And if it's critically damped, what's the benefit of something critically damped? Also, point of it. Shard. Mikhail answered. So you got beat. It won't take that long to decay. The critically damped case is the fastest decay case, while overdamp will decay without any sort of sinusoidal behavior, but it'll take longer than critically damped. That's the big difference between them. So we see that we can learn a lot about our system. And this is for more or less, a very simple system to look at. You can do Newton's second law. You end up with your differential equation, mx double dot plus cx dot plus kx is f or 0, depending if it's free or if it has some external force. And you can solve that differential equation depending on the situation. Now, we want to take a complicated system and model it as the simple vibrating system. Because if we take a complicated system and model it as this simple system up here, well, we can solve that system. We have the equations to solve that differential equation. We know what it will behave like, or we can estimate what it will behave like and predict it. So if we can take something complicated, let's say like, I'll use the example of a diaphragm. And if I can turn it into this, I can ultimately turn it into some sort of circuit that will represent our diaphragm. And that's a really good goal to have, because once we have it in a circuit and we can look at how energy behaves and all those things that are occurring, we can go ahead again and solve for any sort of performance metric that we're looking for. So let's first talk about kinetic energy. If you're looking at, let's say, the kinetic energy of this system, and that's correct, we're using circuits to solve ODEs. That's what the goal is here. By converting this is like our physical PDE situation. We'll do lumped element modeling to make it an ODE, and then we'll convert it to a circuit, which is also ODEs, in order to find our output. So kinetic energy for something like this is just simply 1/2 m v squared, or x dot squared. And the important thing to note is that this m all moves at the same velocity. So if I were to break this mass into a bunch of little differential masses, each one of those specks is moving at the same velocity, because you have this rigid mass that's moving back and forth. So I can look at the kinetic energy of that as being just 1/2 mv squared. But if I'm looking at like a diaphragm, like we have up here, this thing at the center, the diaphragm at the center, has a lot of movement. You can see if this is kind of like the origin, we see that thing deflects the most downwards compared to anywhere else. And if that's the case, it must have a higher velocity if this thing is just moving up and down, because it's going further in the same amount of time. So it has to be moving faster at that point. And then at the walls, what's the velocity at the walls?
0.
Yeah, it's 0, because it's fixed to the cantilever, or to the wall. So for a real system, let's say real, I mean something like a diaphragm or a cantilever beam or something like that, we have a distribution of velocity. And that implies that there's a distribution of kinetic energy. Which is frustrating for us because let's say I had a cantilever beam of mass m and I have a force acting at the tip. Can I say that the kinetic energy of this beam is 1/2 m, I don't know, some x dot squared? Can I use this m, the whole mass of the beam, do you think?
No,
Why not?
because you just said there's a distribution of velocity, so it's going to be different.
That's
each
correct.
point.
Because if we use the m, if we use the whole beam m, what that means is, what it would look like, that implies the whole beam moves as one whole unit. That implies the whole beam moves together, meaning there's literally no wall, it just falls or something. But because it's attached to the wall, because it's attached here, this distribution of kinetic energy doesn't work. Or we need to use this distribution of kinetic energy, as this guy on its own doesn't work. So what we'll do, our goal is to find a lumped mass that does represent the entire kinetic energy of the beam. So I'm going to basically write that we have some K kinetic energy and it's lumped. And I'll say that's 1/2 m lumped times some velocity. We'll talk more about where that velocity, what it is. But by doing it like this gives us the entire, or this gives us the model for the beam. Because what we're doing is we are taking this thing and representing it like this. So this is m, this would be m lumped. This is m lumped. So the whole beam might weigh 100 pounds. If I want to model it as a vibrating system, I cannot use the 100 pounds because the whole thing is not moving at the same velocity. There's this distribution of velocity, and because of that distribution, we are unable to say that this is just 100 here. That doesn't work. You have to figure out the correct representation of that mass to account for all the kinetic energy in that system. You do not want to overestimate it, or your model will be wrong. Does that make sense? So over here, we have some total kinetic energy. And over here is our lumped kinetic energy. And these two things will be equal. Our total kinetic energy will be complicated to find because we have this distribution of velocity. I'm hoping you're thinking about integration, because that's what we're doing here. We're going to be doing that. while our lumped kinetic energy will just be 1/2 mv squared, where that m is the lumped mass, which is what we're trying to find. So that is our goal, is to find the lumped mass. Are there any doubts about what I just said? It's an extremely, extremely important thing that we're going to use over and over again, this concept of lumping. I need to make sure that we're okay right now. So if you have a question, let me know, because I don't think I'll be able to go through this entire derivation that I wanted to in the next 10 minutes. I think it's kind of impossible. We're going to try to find the average spot that finds where we choose that exact spot and integrate it as a constant. Be the same as doing ugly math of the cantilever beam that finds. I mean, that's kind of the idea, is that we're finding some, it's not an average, because the math doesn't end up being some average mass. It's not an average. But we are essentially finding something, I guess, like the average, that it is giving us a representation of this ugly kinetic energy in a more simple way. And once we do that, we'll be able to use that mass ultimately and model it in the circuit, and we'll get there. But that's kind of the game plan here. What I might do in this time, because what we would do next is the cantilever beam problem, which I don't know if we'll have time to do. I might actually just call it now, because I know class ends in like 9 minutes. We'll pick up on this on Wednesday. Are there any questions that come to mind before we leave?
Professor,
Yes.
I have a question on the homework.
Okay, I can stay. Well, I'll stay after to go over homework problems.
Okay, yeah.
Any questions about LEM at the moment? Okay, cool. So, a few things. I'm going to post the professor evaluation survey on Canvas. If you fill that out, you'll end up getting 1% bump at the end of the semester, assuming 75% of the class fills it out, which I don't think will be a problem. We're a small class, and I think everybody's pretty engaged from what I can tell. I don't think that'll be an issue. That feedback is so crucial to me, because this is the first time I'm teaching this class. What I had in mind is definitely not what's happening, considering we lost lots of lectures. The other thing I dropped the ball on that I want to talk about are quizzes. So I have made more quiz problems. I'm going to give you a quiz. The question is, do you want, let's say the quiz options. Quiz options. So quiz idea number one. One giant quiz for note sets 3 to 9, which will probably be something like 15 questions or something, I imagine. Or quiz idea number 2, multiple smaller quizzes. So maybe I do one for 3 to 4, 5 to 6, 7 to 9, or something like that. I don't know. But because I give you the ability to do them twice, 3 to 9 doing twice might be annoying. Then again, you have 3 separate quizzes that you have to do twice, maybe, which is also annoying, but at least you could focus on one set of concepts at a time. So I want to get an idea of what people think. So first person said, feels like chunking it out would play better for all of us. Chunking it out meaning quiz idea 2 or quiz idea 1. Chunking it out I don't know what that means, Logan, because I feel like a giant chunk would be quiz 1, and chunking it out sounds like you're separating it. Quiz idea 2, I see quiz idea 2. Quiz idea 2 sounds better. Everybody's saying 2. Okay. Connor says 3. Okay, thanks, Connor. quiz idea 2. Okay, that's encouraging. So I'll do that. I will post all 3 of these quizzes. I will have them due at some point in the future. I know some of you still don't have power and it's still a mess. I will have them due in the next couple of weeks or so. Get those 3 quizzes done. We do have our exam next week. I'll talk more about that in person on Tuesday or on Wednesday when we actually go back in person in class. Any other doubts? I'm going to stop recording. Okay. If there's nothing else, you can go ahead and lead. If you have questions about the homework, I'll stay on. That's kind of like an office hours thing. I know Austin does, and there might be some others. That's fine too, but I'm going to stop recording. So I hope this was an okay start for LEM. We'll review again on Wednesday. Bye.
Thank you.
Okay.